Alright, in this video we will talk about hierarchical regression, that is the regressive alternative to ANCOVA, basically. The difference is that, for instance, in ANCOVA we would have groups rather than a continuous independent variable. So, for instance, in this case, we are trying to see if practice has an effect on exam grade while controlling for self-regulation. So, controlling meaning self-regulation is our variable. I believe we had similar examples also in ANCOVA, where practice was supposed to significantly differ on exam grade, but practice was grouped according to little practice, moderate practice, or a lot of practice. So in this case, in hierarchical regression, practice is defined by, I don't know, hours per month, hours per year, something like that, rather than having a group instead. So the theory behind it's very similar to ANCOVA, but here we're dealing with prediction, so we're doing a correlational study, for instance, having multiple regression, hierarchical regression. In multiple regression, our predictors were inserted simultaneously. Hierarchical regression, instead, they are inserted, surprise, surprise, hierarchically, meaning we first insert our first predictor, which would be more like our independent variable, and then in a second block we insert our covariate. This is also why hierarchical regression could be called block-wise regression. But without further ado, let's get into the analysis part of it. First of all, make sure that you have three continuous variables, as usual continuous, so change it from nominal. And then we go to regression and we go to linear regression. The first part will be same as multiple regression. We put our dependent variable in here, so what we want to predict, our outcome variable, and then we put our independent variable and our covariate in the covariate area. Let's assume for the purpose of this video that the hypothesis is that exam grade, is that self-regulation will play a significant role in the relationship between practice and exam grade. So this is why we know that self-regulation will be our covariate. The first step, and what will actually change for the most part in the how we tinker with buttons here in Jamovi, will be that we need to go to model builder. Here, as you can see, we have our blocks. This is what used to be in multiple regression, meaning both the predictors entered in the same block simultaneously. So, because of this, we need to remove our covariate, meaning self-regulation, from the first block, and we put it in the second block. I mean, you can also just do like this, that is up to you. Make sure that block 2 is where you have your covariate, and block 1 where you have your independent or your predictor variable. So as the hypothesis, or what we're trying to check, is whether self-regulation plays a significant role, meaning the self-regulation is the covariate, we put self-regulation in block 2, which, as you can see, created here a drop-down menu where you have your first model, so meaning block 1, and your second model, meaning when you add the block 2 part, so when you add self-regulation as a covariate. Now, assumption checks, we have our usual assumptions of regression. Feel free to check the video about that. We close it, we go to model fit, and usually for multiple regression we would prefer adjusted R-square, but as you can see from here, Jamovi gives us a difference in R-square, meaning the difference in the effect size. So for the purpose of doing hierarchical regression in Jamovi, we will use an R-square rather than an adjusted R-squared, even though adjusted R-squared would be slightly better. We need to check our f-test because we want to have our significance and our f-value in the regression tables, and we want our standardized estimate, of course, knowing how much is the standardized regression weight for our predictors. Now it is time to interpret our scales. So I will not focus really much on the assumptions because we already went through them in a different video. So what we need to check first is whether our regression models, meaning this table here, are significant or not. As we can see, both models are significant because both models have a p-value that is lower than 0.05. And the first model has an effect size of 11.5% and the second model of 37.3%. Then we can see from this other table, the model comparison, that the R squared changed by 25.8% and that this change was significant because the p-value over here is significant. Already from this we could sort of imagine that the covariate did play an effect because the difference in R squared is already significant. In ANCOVA we check the difference in eta squared, here we're checking the difference in R squared. Now, here we have the model specific result. So the first one is practice predicting exam grade, and we can see that practice significantly predicts exam grades in model 1 because our p-value is less than 0.05. Then, though, we need to check whether the covariate played an effect. So we switch from model 1 to model 2, and now we can see how the covariate played or did not play a role. We see that practice, after controlling for our covariate, meaning after controlling for self-regulation, becomes not significant because the p-value is greater than 0.05, and we see the self-regulation, meaning our covariate, is showing significance. So this is our final proof that self-regulation indeed had a significant role in the relationship between practice and exam grade.